Okay, yeah, thank you for the introduction. Thank you for the invitation to present at this conference. Well, my topic is going to be a bit definitely analog, but it's very low level. So the title of my talk is Non-Volatile Charge Configuration Memristor and its implementation in a cryocomputing environment. So in today's short talk, I'll briefly present a conceptually unique memory device that we are working on at our department and how we want to integrate it in some cryocomputing environment. Okay, after a short motivation slide, I'll present our so-called charge configuration memristor, or CCM in short, and how it works briefly. And then in the second part, we'll discuss how we can integrate it in a cryocomputing environment by using an additional superconducting amplifying element called a nanocryotron. Okay, so as you know, we've been experiencing huge developments in computer industry for many years now. But lately it seems that computer systems based on silicon are facing more and more problems that make them harder to improve, and there is a wish of finding an alternative technology that would be fundamentally different than CMOS, and there is much research already done in that direction. For example, with the progress on the field of memristive systems, we could be looking into some new technological concepts altogether, such as one-chip memory and storage, biologically inspired computing, and some general purpose in-memory computing. That is why we believe that research on the field of new materials, both from the fundamental side of view as well as the application side, is of vital importance, and this is all part of what we do at the Institute. And it's also going to be the focus of the first part of my talk, so a new material and a new device. But one other possible solution to upgrading computer system is also the use of superconducting electronics, and there is already many components in existence with the exception of a proper memory device. So this means that a memory device that would operate at cryogenic temperatures and would be very energy efficient could present a boost in both in research as well as in performance of such cryo systems. And one example of these system is the so-called single flux quantum, or SFQ circuits, which are driven by extremely small picosecond pulses. We believe that we are able to couple our memory device, or the CCM device, to these SFQ circuits by using an additional amplifying element called a nanocryotron, which we'll see shortly. Okay, so now let's take a look at our devices. So CCM, or charge configuration memristor. The active element in our device is the 1T tantalum disulfide material. You can see we deposit a single flake on a silicon dioxide substrate, and then we fabricate golden electrodes on top using just traditional laser or E-beam lithography. And each pair of these electrodes represents one memory bit of our device. So this is where the information is stored and manipulated. Okay, so how it works. For that, let's first take a look at this first plot, which shows the electrical resistance of our device versus temperature. So as we cool down the device, we go into this, we go through a phase transition into an insulating state, and as we cool down to a low temperature, to working temperature, we get into a high resistance state. So this is the ground state that the device reaches at low temperatures. If at this point we apply a single electrical or an optical pulse, we can switch from the high resistance state down into the low resistance state down here, and we call this process a write process. We can then also, of course, erase from the low resistance state back into the high resistance state by applying a bit longer pulse, which essentially heats up and relaxes the structure, and which returns back into the ground state. So this is called the erase process. So we have two distinct states of resistance between which we can switch. All right, and the typical working temperature is below 20 Kelvin because that is where the device works in this non-volatile regime. This means that this low resistance state does not relax by itself. Okay, we can also look at the switching through the voltage current characteristics that I have here. So first, for the write process, we start in the high resistance state. So as we increase the current, we first follow the black line here until we reach the switching threshold for the device, at which point the device switches from high state to low state, and we can notice a drop in voltage as well in these characteristics. If we then decrease the current, we follow the red line back to 0. Now for the erase process, it's fairly similar, only that we follow the red line in the beginning because we're in the low state. But again, at a certain threshold, we erase from low state back into the high state, and we stay there. We can, of course, also read the current state of the device. We just have to use a pulse, which does not induce any of these two changes. Yeah, we were also interested in examining how scaling of this device works, essentially how the scaling of the device dimensions affects the write voltage in this case. So we fabricated many devices like this, which have varying gaps between the electrodes. And we found out that this write voltage scales practically linearly down to very small gaps. And the smallest device that we've been able to measure, so this gap was 60 nanometers. And that gave us a write voltage of about half a volt. We also wanted to investigate how the switching energy, or energy density in this case, scales with the length of the switching pulses. And we found out that, again, it scales fairly linearly over a wide range, several magnitudes, but at low, at very short times, it deviates from this linearity, which we believe is due to the transmission line losses because our circuits were not really optimized at these frequencies. But nonetheless, we still managed to switch our device with ultra short pulses down to 2 picoseconds, and we also managed to achieve a very good write energy of only 2.2 femtojoules per bit. Okay, great. So I've shown you this memory device briefly, how it works, some of its features, but now let's go into the second part and how we can integrate it, couple it to these SFQ circuits by using additional nanocryotron amplifiers. So first, let's take a look at what this antron or nanocryotron even is. Okay, so this is how it looks like. This is made of a thin superconducting film, like niobium titanium nitride, for example. It has 3 terminals, so drain, source, and gate. It has a channel, and the gate is connected to the channel via this choke region, so a very small constriction. This is how it works. We have a bias pulse which runs through this superconducting channel, and since this bias current is smaller than the critical current of the channel, it stays in the superconducting state and there is no voltage across it. But when we apply a gate pulse to the gate terminal, what happens is that the superconductivity in this choke region is broken, which forms a hotspot, and that in turn also forms a hotspot across the entire region. So this means that the superconductivity in the channel breaks, and in combination with the bias pulse, we now have a voltage that develops across this channel, and we also have some of this bias pulse is being driven through the load, which is in parallel, connected in parallel. Okay, so we can use this antron, and by combining it in parallel to our CCM device, we get a new device that we call a parallelotron or a P-tron. And here is a 3D model of how this looks like. So in black you can see this antron device, and this is the CCM and golden contacts which put them in parallel. And up here we also have some real-life devices of both the Antrons that we use as well as some of our CCM devices. We can also model this device using this equivalent circuit. So our switchable resistor is represented with this resistor switchable, and the Antron is represented with the resistively and capacitively shunted Josephson junction model. Okay, and by using this equation, we can model this circuit and observe the phase phi of the superconducting order parameter, which allows us to extract the steady-state solutions as well as the time dynamics. So for today's presentation, let's look at how the time dynamic looks like for this device. Okay, so first let's look at the simulation. So here on the right, I have a real-life example of one of these Antrons with some annotations just so we can better understand what these waveforms mean. So how this goes is that we have a bias pulse, which is applied here. You can see through the channel in green. And then synchronously, we apply a gate pulse, so to this gate terminal. And in blue, we can observe the voltage across the device, so across this channel, which, remember, it has a CCM connected in parallel. Okay, so what happens at first is when the bias pulse arrives, nothing happens here with the voltage across the channel because, as I mentioned before, the bias pulse is not high enough to break the superconductivity, so the voltage remains at 0. But when the gate pulse arrives, if you remember from 2 slides back, this means that it triggers this choke region, which then triggers the channel, and we do get a buildup of voltage. As you can see here, the voltage starts to evolve with time, and it continues to go until it reaches the switching threshold for this CCM device, which is connected in parallel. At that point, the device switches from high resistance state to low resistance state, which we can observe by the drop in voltage here across the device. And it stays at that level until the end of the bias pulse, when the device is actually ready to be switched, to be triggered again. Okay, so these are the simulations. Let's look at some experimental results as well. First of all, this is how our setup looks like at the moment. So we have separate Antron and CCM devices on separate chips, and we have some control circuit which puts them in parallel, and we can do some other characteristics as well. But yeah, for the experiment, we have a very similar scheme. Now this pictron in the experiment is a bit different configuration, but the proof of principle is still here. So the idea is the same. We apply a bias pulse through the channel, which is 50 microseconds long, and then we have a gate pulse, which is 1 microsecond long. And here on the right, we can actually observe all of this just by using an oscilloscope that we connect in parallel. So we can see it in real time. Okay, so before the bias pulse, of course, the voltage is 0 because it's all in superconducting state. Then when the bias pulse starts, which is here, we do notice a slight increase in voltage. But that is only an artifact of our 2-point measurement. The actual device is still superconducting at this point. But that all changes when the gate pulse arrives at a certain time. And at that point, if you remember, the channel gets triggered. So we have, again, the voltage across the channel starts to increase across the device. And it goes all the way up until, again, we reach the switching threshold for the CCM in parallel, which switches from high state to low state, and we get a drop in voltage that we can observe here. And again, this stays at the same level until the end of the pulse, which, again, after this, the device can be triggered again. Okay, so this is how it works in real time. These are just the preliminary results, because this is actually very recent. But this brings me to my conclusions. So to summarize, I've presented some new device, so this charge configuration memristor, as well as a P-tron device, some basic operations. We've seen that the CCM can be manipulated with ultra-short pulses. It can be very energy efficient, and there is also one thing that I didn't mention, but it's also very robust, so it can easily survive more than 1 million of write erase cycles. It's non-volatile at cryogenic temperatures, so it's suitable for some superconducting or quantum applications. It can also achieve very high contrast switching, and it has a pretty straightforward design, so it's not some complicated structure. And as for the P-trons, we've done simulations that show compatibility with this SFQ logic and SFQ pulses. And we also done measurements which are very promising, so these first experiments. And we've also tested many devices, so many CCM in combination with different entrons, and they show very reproducible behavior, so that's all very promising for future. Okay, at the end, I'd just like to thank all of my collaborators, and I just want to invite any students who might be interested in this kind of research to maybe just write me an email or talk to me later. Okay, thanks.
Okay. Thank you very much. We are running a little bit late, but there's always time for one little question. Yeah, you want me to have the microphone? Can't you hear me like that? Okay. Okay, so we do have time for one more question. A short one. Please. I'll get you the microphone. Well, oh, yeah.
Microphones are for recording because we are recording the sessions. And then you are mute.
Yeah, sure.
And the question is, at these cryogenic temperatures, are you still using normal electronic circuits for the peripheral units around this?
Yeah.
And are there any issues regarding that?
Actually, no. So these are just normal CMOS multiplexers, for example, that we have here, and this is at 1.5 kelvins. So, and it works completely fine. So, you know, cryo CMOS seems to be working completely well. So it's yeah, no issues regarding that.